Okay, now we want to look at vector multiplication. We've seen how to add and subtract vectors. We've done it graphically. We've done it by components. Now we want to look at how to multiply vectors. And it turns out that there's two different ways of doing that. In this series of videos, we're going to look at both of those ways, but we're going to focus on the first way, which is called the scalar product. And we'll do that in due course. Now, when you multiply two vectors together, there are actually two different ways that you can do it. Method one is what's called the scalar product, and the answer is a scalar. Now, when you write out the scalar product, you would write it as something like an A vector multiplied with a B vector, and you're going to get just some number, 17 or whatever it is. And you would actually read this out loud as A dot B equals 17. This is why it's sometimes also called the dot product, A dot B equals 17. But I actually prefer to think of it as the scalar product because that will remind you that your answer has to be a scalar, just a regular number. 12 minus 8, whatever, 1,052. It doesn't matter what number it is, but it has to be just a regular number. Now, there's another way of multiplying vectors together that are called the vector product. And if you were doing a vector product, you would write that as something like A vector cross into the B vector, and that would be equal to some new vector C. And so because you would read this as A cross B equals C, this is sometimes called the cross product. But again, I prefer the name vector product because that reminds you that your answer has to be a vector. Okay, what I want to look at next is how we can actually do the scalar product, what it means and how we calculate it. So what I'm going to look at now is what we call the geometrical definition of the scalar product. And so I've got two vectors here, A vector and B vector. So here's my A vector and here's my B vector. And my vector B makes an angle theta with respect to my angle A. Now what I'm going to do is I'm going to break my vector B into two different components. And I'm going to have a component that I'm calling B parallel that is parallel to the A vector. And then I have a perpendicular component that is perpendicular to the A vector. That means you can see here they make a right angle to one another. And by tail to tip twice, I can say that B parallel plus B perpendicular equals B. So I can replace my B vector with the sum of these two if I need to. Now, if I look at these two components, we can see clearly that B parallel and B perpendicular can be defined by trig. And so I can write out, I've got here the magnitude of B perpendicular, that's its length, is going to be B times the sine of theta. B perpendicular is opposite to theta, so opposite and hypotenuse make sine. If I solve for B perpendicular, I get B sine of theta, where B is the length of the original vector. B parallel is B cosine of theta. And this length, B parallel, that is the length of the component of B that is parallel to the vector A. So what we want to do, if we're going to take the scalar product of A and B, it's given by the length of A, or the magnitude of A, times the length of B parallel. And there's a fancy mathematical term for that. We say that this B parallel is the projection of the vector B onto the vector A. If I had a spotlight up here shining straight down and this B vector were a stick, this B parallel would be like a shadow on the ground. It would be the rays of light coming straight down. This would define B parallel as the part of B that's parallel to this A vector here. So what we can say is simply the scalar product is the length of A times the length of B parallel. And since B parallel is equal to B cosine of theta, we can say that A dot B, the scalar product of the A vector with the B vector, is going to be equal to the A vector magnitude, the length of A, the whole length of A, times the length of B parallel, which is B cosine of theta. And let's note, magnitude of A is going to be a number, magnitude of B is going to be a number, cosine of theta is going to be a number. So you're just multiplying scalars together. The answer of this thing is a scalar. Now, in this picture, I've got my vectors A and B here, and what I'm showing is that I can project B onto A and get B cosine of theta, and that would be the component of B parallel to A. Or I can project A onto B. That would give me a length A cosine of theta. That would be the part of A that's parallel to B. And so if I did it this way, I could note that I would have the length of B times the length of A cosine of theta. That would be the part of A parallel to B. But A, B, and cosine of theta are all multiplied together. So regardless of what order you do it in, A dot B is A, B cosine of theta. I can group it as B cosine of theta. I can group it as A cosine of theta. What this is basically telling me is it doesn't matter what order you do the scalar product in. A dot B is equal to B dot A. And this is called the commutative property. We've seen this before with addition under vectors. It's an important thing to know. If I tell you to give me the scalar product of two vectors, it doesn't matter what order you do them in. Now we also want to be able to apply the scalar product to vectors that are expressed in component forms with their unit vectors. And so we want to see how we can apply the scalar product when we have unit vectors. So if I have a vector A, I can represent that vector A as AX in the x hat direction plus AY in the y hat direction plus AZ in the z hat direction. Any vector can be represented that way. Now, what is AX? That's just a number, 15 minus 2, whatever it is. And that would be the x component of the vector A. AY would be the y component, AZ would be the z component. Now the unit vectors are vectors with magnitude 1, so we can see all of them have a magnitude equal to 1, but they're special in that they point along the Cartesian coordinates of the Cartesian coordinate system. So x hat points along the x-axis, y hat points along the y-axis, and so on. And as we can see, all three unit vectors are mutually perpendicular to each other. That means that two different unit vectors, x hat, y hat, or z hat, if I pick any two of those, they're going to be perpendicular to one another. So that's going to be important as we see. So what I want to do in this slide is I want to actually see how we can apply the scalar product and multiply unit vectors together. And so there's two possibilities if I'm using x hat, y hat, and z hat. I can multiply the unit vector by itself, x hat dot x hat, and this could be y hat dot y hat, z hat dot z hat, it doesn't matter. I've got one unit vector multiplied by itself. Now, from the geometrical definition of the scalar product, I can say that that's going to be the magnitude of the first vector, x hat, the magnitude of the second vector, times the cosine of the angle between them. But what's the angle between x hat and itself? 0. There is no angle between x hat and itself. And so the cosine of 0 degrees is 1, so x hat dot x hat is just 1 times 1 times 1, or 1. Now what if I take a couple of the perpendicular unit vectors? I could do x hat into y hat into z hat, x hat into z hat in any order, but we'll do x hat into y hat. And so this is x hat dot y hat, and oops, I just noticed a mistake. This guy here should be y hat, not x hat. So x hat dot y hat should be x hat magnitude, y hat magnitude, the cosine of the angle between them. And so what's x hat magnitude? Well, it's a unit vector, so I get 1. What's y hat magnitude? It's a unit vector, so I should get 1. But what is the cosine of the angle between them? The cosine of 90 degrees is 0. And anything multiplied by 0 is simply 0. So any perpendicular unit vectors is going to have a scalar product equal to 0. And by the way, this is a big tip. Anytime you're asked to find two vectors that are perpendicular to each other, one way to do that is to use the scalar product. If you set the scalar product equal to 0, then you know that that means that the angle between them is going to be 90 degrees. So to have two perpendicular vectors means that you have two vectors with a zero scalar product. And so just keep in mind, anytime you're given a problem where it says something about the vectors being perpendicular to each other, that's a flashing red warning sign that you're going to need the scalar product, most likely. But let's actually apply this. A vector is equal to ax x hat plus ay y hat plus azz hat. Similarly, b vector is bx in the x hat direction plus by in the y hat direction plus bz in the z hat direction. Now, I could have done an example with numbers, and I will do this in class, but this is the most general form. So ax, ay, az, bx, by, bz, they represent any numbers, positive or negative, that you want. And you just plug them in. Now, if I take the scalar product, a vector dotted into b vector, I could write my a out long form, and I could write my b out long form, and then I want to just multiply them out. And how do I do that? Well, you basically do the FOIL method from algebra, and of course there's more than two here, so it's not quite FOIL, but you get the idea. I'm going to take that one, and I'm going to multiply it by those three. And when I say multiply, I mean I'm taking the scalar product. So I'll do x hat, so ax x hat with bx x hat. I'll take the scalar product of ax x hat with byy hat. I'll take the scalar product of ax x hat plus bzz hat. And you can see that that's exactly what I did in this first line. I've got ax, bx, x hat dot x hat. So it's ax x hat dot bx x hat. I pull all the scalars out front. That gives me x hat dot x hat. And what is x hat dot x hat? If you remember, that is equal to 1. Any unit vector dotted into itself is 1. Now, if I continue, I can note that ax, by, x hat dot y hat, any two vectors that are perpendicular, you take their scalar product, you're going to get 0. So x hat dot y hat are perpendicular, you get 0. X hat z hat gives you 0. And I can just keep going on a line. This is going to be 0. But y hat dot y hat, that's going to be 1. So I'm going to have that's going to be 1. This is going to be 0. That's going to be 0. That's going to be 0. So all these terms cancel except for the ones that are the unit vector dotted into itself. That one's going to be 1, z hat dot z hat. And so when you cancel all the terms that go to 0, you end up with a dot b is ax bx plus ay by plus az bz. And we'll look at some examples in the next video.